Joining us today. The Center for Connected Multimodal Mobility is very excited to introduce you to Dr. Richard R. Brooks, who is a professor of electrical and computer engineering at Clemson University in Clemson, South Carolina. He's senior member of IEEE and has written a couple of books, Disruptive Security Technologies with Mobile Code and Peer-to-Peer Networks, An Introduction to Computer and Network Security, Navigating Shades of Gray, and as well as co-writing The Multi-Sensor Fusion. He's edited several books as well. He's worked with reactive sensor network projects sponsored by DARPA, and is also one of our project principal investigators. So Dr. Brooks is working on one of our C2M2 funded projects, and we're very excited to have you speak today. So with that, I'm going to go ahead and turn it over to you.
Okay. Hi. This talk actually was sort of put together as a tutorial, and it brings together things from a lot of my projects. I have the chat window open, so if while I'm talking, if there's like some points that aren't quite clear, feel free to, you could say, send everyone a chat, or you can send a chat directly to me if you should be concerned about, you know, I don't know, showing everybody that you don't, that there was something you weren't getting or whatever. But if I get, I like for it to be as interactive as possible. So if you have something that you want to put in there, that'll probably work better than, say, using audio. Although I'm fine with your using audio as well. But in this format, probably the chat is better. This work, I also mentioned a couple of students who've worked with me on related things. And I'm going to go through a number of different projects that I've worked on with this and how my understanding of the problem domain has evolved over time. And so I will start with the DARPA JFACC project, which was JFACC stands for Joint Forces Air Combat Control. And the why DARPA started the JFACC, well, the JFACC program, was they wanted to integrate control theory into command and control. Traditionally, command and control, basically you could, the command and control technologies were basically communications. But they noticed in air combat with the war in the former Yugoslavia campaign, the air combat missions planning and execution took 3 days on the average. So you would have a target that was identified. You would have a briefing for the pilots. The pilots would fly out and attack the targets. And typically, the fighter bombers, the pilots come back and they're convinced that they've accomplished their mission and destroyed the targets. And then the next day, you would have the surveillance assets, frequently satellites, go over and take an assessment and see what actually happened. And then you'd have evaluation of that, and then you'd have a new briefing, and then the pilots would go out again. The enemy caught on quickly to this, and they actually knew when the satellites would be flying overhead. And for example, if you had mobile surface-to-air missiles, if they weren't destroyed, the enemy's not stupid, and they're not going to leave them where you tried to bomb them last time. And they would move them to another position. They would move them to the other position after the surveillance assets went over, so that the 3-day lag time effectively made it very, very difficult to have an effective air combat campaign. So what the Colonel McCory was the head of this project at DARPA. His idea was to integrate control theory into command planning and execution. In control systems, you don't separate the sensor feeds from the actuators. The actuators respond in real time to that. So why couldn't you have that with the military systems? Why do you have to have the surveillance assets fly over and you evaluate them, and then based on that, why can't you just take the feeds in and then decide what your assets are going to do at the same time? And when you brought control theory into the combat system command and control, that of necessity brought in game theory. There's a long history of game theory and control theory. Control theory basically being that you have sensors and actuators, and the actuators respond to the sensors, and then you also have noise models. Game theory started with von Neumann in the 1940s, and it's the basis of a lot of economics, but it's basically the idea that you have different participants with different incentives, and for you to respond properly, you have to understand the incentives of the opposing side. So you can look at that as an adversarial control problem. So again, in the combat scenario, you would typically think of it as what's known as zero sum, which is what's good for me is bad for the opponent and the other side. I think there it's fairly clear what the opponent is going to be doing is not a it's not a normal distribution. It's not a Gaussian distribution. The opponent is going to have goals that are different from yours, and for you to figure out how you should handle that, you need to take their incentives into that. So the different approaches that were considered, discrete event control is for those. Okay, I'm assuming that we have a lot of engineering students here. But discrete event control is more a finite state systems, and so instead of most traditional control theory is that you have actuators with continuous variables. You have sensors with continuous inputs, and you then work with that. With discrete event control, you have finite state systems, and you have different actions that can be taken to move from one state to the next. Hybrid control brings in the discrete event control and the continuous control. Frequently, that could be that you have a set of continuous controllers, and you can switch between them based on the mode of the system. H infinity control is also called robust control or optimizing control, and a part of that is that you have different types of metrics that you're using for that. A very common way of doing that is if you have a control system where there are multiple attributes that are being considered, and you have, let's say you have a 5-dimensional system where there are 5 different attributes that you consider, and then you have a nominal signal that you're trying to follow. So you would have, say, a line in the 5-dimensional space. You would try to choose the one that minimizes the deviation in all of the dimensions, so that you have, again, you have a nominal signal in the 5-dimensional space, you would figure out the expected positions in the 5-dimensional space, subtract the position in each dimension, and try to minimize the deviation in each dimension. Another thing that was done was communicating automata, which is for those of you that are familiar with cellular automata, it's like that, and you have a bunch of state machines. They're exchanging information, and they all react in response to each other. Another approach, which that's sort of taken off since this project, pheromones. If any of you are familiar with ant colony optimization or any of the things derived from that, it basically insect societies are driven by hormones that are received with a sense of smell. And the thing that's interesting about that is it's a learning system, but it's a learning system that has forgetting built into it, which is actually learning or being able to discard information that's out of date is a very, very important attribute for any of these things. Another approach was basically for each combat mission, you would set up an auction. So you would have different missions, and each of the combat pilots or groups of planes that would be sent out together would put in an auction for the different missions. One thing that was interesting about that was the project, you had a bunch of academics working there, and then they also had SMEs, subject matter experts, who were former fighter pilots who were there to give us advice. And the funny thing about the auctions was that all of the academics were talking. We were saying that just made no sense because, if you had a set of missions and one of them was much more dangerous, what would keep people from lying and saying that they weren't very well suited for the dangerous mission so that they wouldn't die? And then the fighter pilots, when the problem was exchanged to them, they said it's not realistic because what's to keep people from lying? And all the fighter pilots would put in bids that were unrealistic for the most dangerous missions so that they'd be more likely to get the dangerous missions because they're adrenaline junkies. So that was just sort of an interesting difference between the different social groups. And then another approach was linguistic geometry, which is from Professor Stillman. He was at the University of Denver. I don't know where he is now. He immigrated from Russia, and it was basically an automated system that modeled everything as you could basically see it as a form of chess. And so it would do it would look at the different moves that would be possible for each piece on the battle space and do a depth first search. And this is for those of you familiar with control theory, this is the problem space that everyone ended up with. You start off with, you have the plant in the middle, which is the environment and the environment with the different players. So the friendly combat forces and the enemy combat forces. And on the top you have the enemy. So K would be the enemy deciding the actions that they're going to take, where they're going to move their assets, if they're going to attack, if they're going to hide, where they're going to turn on their sensors and so on. And the delta above that is noise. So you have the plant, the environment, you have going out of the plant and into K at the top. So those are the sensor feeds that the enemy has. K is the enemy's making their decision. Delta are the noise factors. Again, the top delta is the noise factors that the enemy has. And so that's the enemy's choice for their next move, okay? And then the delta at the bottom is the noise factors for us. So that gives us a new plant, P prime, and the new plant includes the enemy. So you have the environment and the enemy and the noise factors for both sides, and that's actually what you're trying to control. So you're trying to control what happens in the environment, but you're also trying to control what the enemy is going to do. So you have then your sensor feeds coming out of that, and the K at the bottom is your local controller, and then the ST at the bottom is you also have a set of other assets, of the friendly assets, and what they're going to be doing. So you have to have your control, what you're going to do in the next step, and then you also have to do some consideration as to what the rest of your group is going to be doing. Okay, and that changes the problem. There's also an issue in that if the enemy controller is as powerful or more powerful than yours, then the problem is not going to be one that you can control. It's going to be unobservable, it's going to be uncontrollable. So there are limits to what you can do. But it's a very useful way of looking at a larger class of problems. So what I took away from this is it's an open problem, and it's a problem that's probably never really going to be solved. And the biggest problem with this in terms of using game theory and where game theory is problematic for most military systems is the state space is undefined. The way game theory works is you know the set of actions that can be taken by both sides, you know the payoff functions, you know the incentives for both sides. So, if I know the actions that the opponent can take, and I know the actions that I can take, and I know the opponent's incentive structure, and I know my incentive structure, then you can predict to a certain extent what the opponent is likely to do, or at the very least, except for certain classes of continuous problems, but for non-continuous problems, there will be a so-called equilibrium solution. So you can find a solution where if you do one set of moves, there's a defined other set of moves that the opponent can do, and the opponent is not going to improve their standing by doing anything other than the moves in the equilibrium solution, which is good. But again, in these problems, you don't know what the opponent's incentive structures are, and typically, if you have a well-defined and limited set of actions that you think the enemy is going to take, that's not always a good bet. Actually, it's frequently a very bad bet. And that's why, again, that's always been the problem, is having is defining a lot of moves for both sides and the payoff functions. And what often happens with this, with a lot of the game theory research right now, Um, there's basically two classes of game theory research. For mathematicians, they will basically prove whether or not there's a solution to the problem. They won't bother trying to figure out the solution to the problem. They won't give you practical tools for dealing with it, but they will tell you whether or not the problem could be solved. Okay, I'm in an engineering department. That doesn't seem particularly useful in terms of research or results. What you get on the other hand are a lot of people doing research where, again, the state space and the incentives aren't well defined. And so frequently what they do is they come up with models for the problem based on sets of equations that they know how to solve, so that they can solve the problem, but there's no reason to believe that the problem is the actual problem that's being posed. That's where lately there's been a field called behavior economics, where they've been looking at a lot of economics that's based on game theory, and they examine it and they find out that the problems that people are actually solving are not the problems that the economists think that they're solving. So that's for control systems. Okay, for these problems, the environment, which includes the enemy, can adapt and learn, which makes it more difficult as well. You have the adversary, and another thing is to consider the controllers are often part of the hierarchy. Coordination between multiple platforms is difficult. For controls, you do need to have the idea of game theory. And another thing is to think about in military systems, and this depends, okay, you have the idea of tactical, operational, and strategic logic. Interestingly, between the different branches of the armed forces, tactical is defined the same, but for some of them, operational and strategic are switched, which makes talking with the military leaders even more fun. Tactical is along the lines of I have a gun and there's another guy with a gun and we're both trying to shoot each other. Okay, so that is very short term, small number of pieces involved, but it's just immediate. Operational would be like logistics. So if you have a set of 4 or 5 groups in the field and they're involved in tactical engagements and they need to have plans and tactics for the tactical engagements, operational is figuring out how to get them what they need, how to get them the food, medicine, ammunition, and so on. And both sides have to do that. And that's longer term. You have to consider other things. And that's also, quite important. Frequently with the operational, you would try to, if you have like a group of soldiers on the ground and they can't get any food, if they can't get any food or ammunition, you'll be able to beat them. So that the operational is a different level of logic. And then strategic is a level above that. That's like nation states and whether or not you should engage in warfare or possible use of nuclear warheads and so on. So you end up having, basically they divide it up into those 3 levels. As I said, I forget which branch of the armed forces, strategic is the top and operations in the middle. There's at least one that flips that, which makes discussions fun. So game theory, or figuring out what the other vehicles, assets, whatever, what the other players in the problem are going to do is essential, but there's also multiple types of game theory. And I'll just bring in now, you should also think, if you know, since we're talking about transportation, think about this also in terms of autonomous vehicles. For me, with an autonomous vehicle, to figure out where I should steer my car, I kind of have to think about what the other cars are going to be doing. One of my favorite quotes with autonomous vehicles was a story, I think it was the New York Times, maybe about 6 or 7 years ago. They had one of the Google engineers who was working on implementing autonomous vehicles. And he made the all-time great statement that for that all of the human drivers on the road are going to have to learn how to drive differently in order to get along with his autonomous vehicle. And that points out the problems that we're having with some of these systems, and particularly in terms of the autonomous vehicles. If I implement an autonomous car with the assumption that everybody has to learn to get out of my way, I suspect that we might have problems in the future. Okay, the next project, I had an Army Research Office math grant, which extended the work we had done in JFACC. We looked at coordinating teams of air combat vehicles, and what I basically did was I took the approach we had there, I put in more game theory and created sets of interacting players, and the idea is that you would have continuous sensor feeds, and then each platform in the problem would have differential games, so that you could think of it. We took as a challenge problem, a thing that we had that we looked at with the JFACC problem. It's called suppression of enemy air defenses, SEED, and the approach that the U.S. military prefers to take, if they're engaging an enemy country, the idea is that first you do air combat, and you send in, because we typically would have air superiority, we want to take advantage of that and use the air superiority to destroy the ground forces before your ground forces go in. It's just a cleaner and more efficient way of handling it. But before you send your bombers, you want to get rid of the enemy air defenses. And so the enemy has a set of surface-to-air missiles. It would be a lot easier if you knew where the surface-to-air missiles were located, but typically you don't. And so they have special combat vehicles called wild weasels. And those are actually what they do is they send the wild weasel out there, and it flies around and it waits for somebody to try and shoot a missile at it. When the enemy air defenses start, they turn on the radar. You can locate the fact that you're in the enemy's radar, which gives you some warning, and then they will fire the surface-to-air missile at you as quickly as possible. I found it kind of interesting. The best strategy, if you're in one of these vehicles, to survive is to fly directly at the surface-to-air missile. And if it just barely misses you, then it cannot turn around and catch up to you again. If you try and run away, the missile's faster than you are, and it will track you down and kill you. So what we were looking at was, if you were to have a vehicle like that with, let's say, 3 or 4 drones with you, how you could coordinate them. And if you've got like about 5 vehicles and you're trying to figure out all the possible motions of those vehicles and coordinate that in real time, that's actually not a very practical way of doing that. So what we did was, for each of the vehicles, we would we would give them a small set of strategies. That means if I'm, say, one of the drones and I have 4 possible actions that I can be taking, I can solve 4 or 5 game theory problems in real time, and I can figure out my expected payoff. I could figure out the likelihood of survival, likelihood of killing the enemy, or whatever combination is my payoff, right? And then the 5 friendly vehicles, all they have to do is exchange those payoff values, and then you've got a very simple logic, right, for choosing who does what. You just, the things that are most important, you give to the ones with the best score, and you basically have some sort of, it could be an auction of some type between them. And so then the network protocol exchanges the differential gain value, and you have an operational layer for that, which uses the strategic form game theory, which is where you have a matrix of the different possibilities and the different payoffs, and you decide who does what. Okay, and so that allows them to have a sort of a distributed supervision. And games that we looked at, this is a pursuit evasion game. So that is, if you have, let me go to the next one first. So if you have, this is your car, and if you have a car, you have, okay, think about this. This is the thing in the middle is a car, and then with the front wheels, or it could be the rear wheels, whatever you use to steer, there's a limit to how tightly you can steer, right? So you cannot go directly into this circle. And then also, okay, you can accelerate, and if you're going straight, you can accelerate, there's a maximum speed that you can reach. But when you turn, the more slowly you have to go. And then, I mean, once I'm here, I could go back there. So for any place in the problem space, you can figure out and that's this here on the bottom left, you can then figure out the fastest path to a point in the problem space. Going back to here, the basic issues that you have with a pursuit evasion game is you have one car chasing another. It's also called the homicidal chauffeur problem, and that is you have one car that's trying to ram the other car. And the parameters that you typically had were current velocity, maximum acceleration, deceleration, and the turning radius. The K, capital K, is the turning radius, and then there's also a limiting turning radius, which is where your car is going to roll over. Okay, and the traditional view was basically if you could turn faster than the other car, you're going to stay alive and you're going to win. And if you both, if you're the evader and you cannot turn more tightly than the other side, then it's going to look at who's the faster car. Okay, and there's some more calculations in the middle to decide, but basically the more maneuverable and faster car is going to win. What we did here is we changed the problem somewhat because the pursuit evasion game, as they had it defined, basically your strategy, if you're trying to run away from the police, the strategy is you would go into the street and just run as fast as you can for the rest of your life, which is not a particularly good strategy because you'll eventually run into another policeman and there's a limit to how long you can run. If you want to effectively avoid the police, okay, if a policeman's right there, yes, you're going to run away from the policeman, but then you're going to try and blend in with the crowd so the police know where you are. So what we did was we added sensing to the problem. And so here, if P is the pursuer and E is the evader, and P is the sensor, then the evader would typically want to go someplace where the pursuer cannot tell where they are. Problem with that is, oh, I'll go back. I'll stay here. Problem with that is the effective sensing range. For like radar, effective sensing range falls off as 1 over r to the 4th. If it's a camera, it falls off as 1 over r to the cube, 1 over r cubed. If it's acoustic sensors, it typically falls off as 1 over r squared. But the trick is the strength of the signals that you're using falls off, but there's not a magic range where you can detect everyone inside the range and you cannot detect anyone outside of the range. If anyone presents something to you that is phrased in that way, feel free to ignore the rest of what they say because they're totally uninformed. What we did, however, it is true that if I have a radar here, I cannot tell what's going on in Shanghai. Okay, so there is an effective sensing limit, but it depends on a lot of things, and it's definitely not the line that you see there. But what we did was, since your true positive rate is going to fall off as 1 over r to whatever, but typically the trick is what the false positive rate is, which you really can't know, but the typical way that they model this in engineering is to have a constant false alarm rate. So you have a constant rate of false positives, whereas the true positive rate falls off. And once you reach a distance where the signal coming back is more likely to be a false positive than a true positive, then logically you should ignore what you're getting. And at that point, that's what we're calling the effective sensing range. Now we're then looking at it as a Bayesian probability problem. So that is, if I'm the pursuer and I have some idea as to where the evader is going to be, right, then I can combine a sensor reading I'm getting with where I think they could be, and that might make my trust in the value that I'm getting such that, even though it's beyond the effective sensing range, it's a pretty good chance that it's going to be there. And so we did that, and we solved these problems. That was a fun problem, and we had 2 different strategies for the pursuer and the evader. Strategy number 1 is basically the run as fast as you can. You try and figure out how you can get further away from your enemy, or how you can stay as close. If you're the pursuer, you want to go to where the enemy was, where you knew that, and you want to get there as fast as you can. And if you're the evader, you want to get as far away from where the pursuer is going to be as you can. And that's the PER. It's marked there. It's the traditional answer to that. And for the evader, we had the strategy of getting as far as you can, and the alternative solution is a maximum entropy solution, where if I'm the evader, I can figure out the probability distribution that the opponent's going to have after they have the sensing information, and I can figure out their belief function for where I'm going to be, and I want to maximize the entropy of that. So I want to decrease the certainty of where they think I'm going to be, which is basically, when I describe the problem with running away from the police, I want to blend in with the crowd. So the policeman doesn't know where I am. And effectively, the policeman doesn't know where I am, I'm safe. And we then analyze this. And the thing that was interesting, so we did a number of simulations with evaders and the evaders with these. And the best solution for the evader is to maximize the entropy, which makes sense, right? So that the other side doesn't know where it is. And since you would think that this problem is a zero-sum problem, you would think that if the evader, you would think anything that the evader does to hide effectively would be their best thing. And so what the pursuer can do against that would be the best, right? So that anything player one does that hurts player two would be to its advantage. Anything player two does to hurt player one would be to its advantage in the same amount. Strangely enough, we found that this is not a zero-sum problem. The pursuer should use a different strategy and to a certain extent play a totally different game than the evader. The pursuer should go to the last position where it knew where the evader was. That helps them. Okay, and then this is getting back to what I was talking about. This is the suppression of enemy air defenses game. Here we're looking at, this would be a aerial drone that's looking to fly in and shoot a missile at a surface-to-air missile, and this would be the surface-to-air missile, which is looking to shoot down the aerial drone. And if you have, and so this is a continuous time problem with continuous sensor feeds, and then also with continuous actuation. And that's a difficult problem to solve mathematically, and you may not even be able to have a solution. What we did though, which is something you have frequently in finite elements analysis, which is how most people solve differential equations in reality nowadays, is that you can then look at, okay, if I go with different speeds, I will be in different places in here, and then also with a different turning radius, so that I can take the two continuous variables and actually turn it into a set of boxes as to the places where I could be. And similarly, for the surface-to-air missile, you can look at how quickly it would turn in different directions and when it would fire and when the missile would be in different places. So you can then have a matrix of different voxels, different places where the missiles could be. And if the missile and the drone are in the same place at the same time, then you would have a probability of the missile shooting down the drone. So then in that way, you can take the continuous time differential game and you can reduce it into a matrix where each player has two different choices that they can make, and then you've got a well-defined payoff function for that, and that's how you can solve that. So then each player in the game there, where we have one surface-to-air missile and about 4 or 5 drones, you can then have them figure out what's the best best way of doing that. And then here's the way that we then switch this into, into a simple flow chart. And then you can use game theory and linear programming to figure out the payoffs of the different solutions. And again, you have predictions and you can come up with a solution. And each asset that's working together can solve its own problems. You just have to exchange a very, very small amount of information with that. And when you do that, you can solve a very complex coordination problem. This is another problem that we looked at. This is based more on this problem was if you have a set of about 4 or 5 air combat vehicles and they need to coordinate what they're doing, and they need to exchange information as to how useful it would be for them to have another airplane where they are, but there's limited bandwidth. So you have to decide who has the channel. Now, unfortunately, if you're exchanging information, then you're using up the channel, so it wouldn't be available. And the problem that we're solving here is basically a sum of games problem. So if you have like 5 air combat vehicles fighting 5 other air combat vehicles, and you have to decide which one of the planes is going to be able to communicate, it's equivalent to, say, playing 5 games of checkers, and you have to and you can decide, I'll move in one game now, and then the next player can choose which game they move in. And where let me see, normal combinatorial optimization problems are intractable because they're too complex. They're an exponential problem. They're exponential in complexity. These are exponentially exponential, so this is much more complex. However, you can find a solution. There's a thing called surreal numbers, where you can solve the sum of game problem, and this allows you to have a solution that's within constant offset from the optimal solution. I'll start moving forward more quickly because I'm running out of time. Then we looked at my internet. If you're having trouble because of my internet connection, let me know, and I'll go back through it. This was then a problem that we did for ONR, where we looked at learning different behaviors of the enemy and developing strategies based on what we learned. And that became competing Markov decision processes, so that you have a set of states and you have a set of possible payoffs, and then you make decisions based on that. The final product of that project, which we're pretty happy with, is we found a way of using the competitive Markov decisions processes and information that we got from shipping traffic. We learned how to infer the shipping patterns off the coast of Florida. My co-PI spent some time at a naval base in Key West using their sensor feeds in the skiff, and we learned how to predict where a ship was going to be 4 or 5 days in the future within 2 or 3 nautical miles. This was then transitioned into the fleet, and eventually NATO is using our logic for that. Okay, as we move on, so we went from air combat to the Army to the Navy. Now, if you're looking at like the smart grid or assisted vehicles, it's the same problem. As I said, with this car, if it's figuring out where it's going to go, of course, unless you're an engineer for Google, and then the optimal solution is everybody better figure out where you're going and get out of your way. But if you're a sane person, if you're trying to figure out where this is going to go, you need to try and figure out where all of the other vehicles are going to be and not be there. And so the cyber physical systems, you have a physical plant where you have an interconnected systems with multiple players involved, a lot of sensors and actuators. You have global and local communications systems, and then you also have intentional disruption, you have fraudulent information, or denial of service, code data insertion. A good example would have been Enron, which used to be the broker for electric power through large parts of the US, artificially produced blackouts in California so that they could increase the prices for electricity. So if you're designing a cyber physical system, you have the physical part, you also need to think about different problems people could introduce intentionally. You have to think of the actions of everyone else involved. You also have to think about potential bad players. And then you also have to look at potential disruptions of the sensors and actuators. The work that a lot of this was based on is then kind of based on when I'm hearing a lot of people with their plans for autonomous vehicles, I just think that they're unrealistically optimistic, so that, for example, with platooning problems, you've got, there are a lot of implementations that have been done on that. So you have this vehicle here, and it's in the middle of a set of vehicles. And the idea is the lead vehicle would drive, and the vehicles behind it would drive closely enough that they can take advantage of the reduced air resistance, but then they'll also want to keep safety, and then everybody can save on gasoline. One of the problems I have with that is that if you're doing that, you have to assume that all of the vehicles are going to be functioning correctly. And when I think about the highways that I drive on, if you're going to create a platoon with around, say, 13 vehicles that are then coordinating their activities, you're kind of assuming, or I think the people that are implementing it are assuming that all of the vehicles are well maintained, all of the vehicles have, all the vehicles are well maintained, they all have the right level of software, they're all functioning properly, and nobody's trying to do anything bad, which I think is in general not a very reasonable assumption. So I think a better way of designing systems of this type are to first design a nominal system that's supposed to work the right way, and then analyze the system by introducing controllers that are not going to function properly. And in fact, controllers that are designed the opposite of what you're trying to do. And then you use game theory to redesign the other controllers so that they can tolerate the problems. And we looked at the as an example problem. Another problem that you could look at is then accident avoidance. I'm kind of worried about the systems that they're implementing now because if you're assuming that everything's going to work properly, there are currently people that drive along the highways and create accidents on purpose as a form of insurance fraud. And if you have automated systems that are designed naively, it would be very easy to figure out how the vehicles are going to react so that you could cut somebody off, force them into an accident, and then voila. And so here's then looking more at the thing. I think I'm just going to, here's with this, we then set up, we put together a bunch of different sensors in the problem. We had the measurements, we looked at that. We then looked at different types of errors that you could introduce into the system. And we had nominal, the miles per gallon that you could get if everything worked right, the amount of improvement that you would get. And then we put together a few simple controllers, centralized, they got all of the information, or decentralized, everybody makes their own decisions. And then we came up with a few different techniques to help you avoid the problems that you could get. And we ended up, when we now analyze that, this was the matrix that we got at the end, where I think iChart is being too kind to that. And then we used, since we used simulations to determine the likelihood of a problem occurring, so we produced a matrix with combinations of different strategies for all of the players involved, and then you would end up with a mean value. But again, if you're using simulations and looking at the number of times you had accidents, one of the main problems is whether or not the outcomes that you get are statistically significant. So we use z-test to find the 95% confidence interval as to whether or not two values are the same. So if one value is significantly higher, then we would say that solution is better. If it's significantly less, then we'd say that solution is worse. And otherwise, we would say that they're functionally equivalent. And then the next thing we looked at was domination, which is if you have one strategy that is worse in all situations, you can remove that from the problem space, because no one would ever choose that, and you can do that recursively until you come up with a smaller matrix for the problem. So we did that, and we ended up actually with saddle points, which is there was a solution which was the best solution for that. And so for the miles per gallon, if you wanted to, and also for maximizing the savings with gas, and also for minimizing crashes, the worst case for all of them was then adding a lot of noise, and the best countermeasure was to have controllers with Kalman filters embedded in them. For miles per gallon, actually, it was a centralized controller. For avoiding crashes, it was the decentralized controller. And so then the lessons learned, the crashes in the miles per gallon were mainly affected by actuator noise rather than the sensor noise. The Kalman filter for combining the sensor feeds was the performed better, and also the saddle point, which was the best choice for crashes, was not an acceptable solution, because we would end up with more crashes than you'd be willing to allow. And so the idea is to, more work is needed where you add more sophisticated type of disturbances, and we need to modify the payoff function. And yeah, nobody wants a platooning situation for saving gas that is dangerous for them. So the basic takeaways that I would like for you to have is, number one, if you are designing a control or autonomous system that's going to function in the real world, you need to come up with some sort of game theory approach for figuring out what the actions are going to be for the other participants. And you should also then, in doing that, try and consider amounts of noise or different failure modes for all of the participants in the system. Okay, I'll open it up for questions now. Okay, specific game theory used and how many players. In all of them, we reduced it. Okay, we reduced the actual conflict to a two-person game, and two-person would be, okay, for the platooning, you would have, okay, for the platooning, you would have the normal people that want to save gas and not have crashes, and you would have a set of disruptors. For the military applications, the idea was that you would have, say, friendly forces that are working together and enemy forces that you're opposing. So, like, say, two nation states. But within that, you would have different individual assets that are coordinating their activity. Game theory, two different types, well, actually no, three different forms of game theory that we used. We tried to avoid differential game theory because solving that in real time is not a good idea. And what we generally did was we would try to reduce it to the strategic form. We had matrices with, for both sides, the set of possible moves and then the expected payoffs. A lot of times we ended up with competing Markov decision processes, which you can then translate into the strategic games frequently. The one with the thermographs is a different type of game theory, and that's based on the work of Berlekamp and Conway. Berlekamp died like about 2 or 3 years ago, and Conway died only a few months ago. But it's very interesting because it's a combination of number theory and game theory, and the surreal numbers are very, I would be willing to bet that almost none of you have heard of surreal numbers, and to do the analysis, there's a really nice graphical approach. But it gives you, in constant time, you get an answer within a known offset from the optimal solution, which is really great. Okay, Mahfouz. What happens if the number of enemies are very large? Does it affect the computation? What are the possible ways of solving this issue? Okay, it's the same problem for both sides, really. And what you would, again, the way we handled it would be to reduce it so that each player computes the possible solutions for them, and then you exchange those. Now you're right that if that's and that works better for you because you can then exchange the numbers. If you're doing that for the it would end up being the same thing though, because for each asset considers the possible movements of their opponent, and that's baked into their solutions. So they're looking at it tactically. And then the operational problem is by exchanging that number. And that's the best you can do. And probably, I hesitate to think that you could do better than that probably because the solution on the other side would require you making assumptions about information that you can't have. So I just I would go with that. Okay. Zadid Khan. Game theory is more systems with more uncertainties. Or is there better with any level of uncertainties? Oh, the Donald Rumsfeld problem. Yes, he was the one that talked about you have systems with, you have known unknowns and you have unknown unknowns. So with uncertainties, which kind of gets back to the problem I said with the military systems, because you generally you don't have a well-formulated problem in terms of what the enemy's possible moves are, and particularly what the enemy's goals are. Now, one way of handling that is to just look at your goals and assume that it's zero sum. But there's a problem with that, like we saw with the pursuit evasion problem, right? Where it's not really a zero sum problem, and that's where I like the way we handled that. That was the pursuit evasion problem. Okay, it's my own work, so of course I like it, or I wouldn't have done it that way. But with the pursuit evasion problem, when we looked at that, people have been working on that since the 1940s or 1950s. But the assumption was always that the pursuer knew where the evader was. And we were the first people to build in the idea of sensing models, where there's a limit to the information that you have. So actually with that, I would suggest building in models of your ability to gather information and try and adapt the problem to also consider the sensors and the actuators more. Okay. I'm happy to answer more questions if there are more questions, but I think I've actually gone over time anyway, haven't I?
Yes, we are a little over time, but we do appreciate you taking the time to kind of answer all these questions. As I said earlier, this talk will be posted on our YouTube and our website, so people can always get in contact with us if they have more questions.
Mm-hmm.
Appreciate your time.
Thank you, Richard. Thank you, Richard. It was a super presentation. Thank you.
Okay, and you can also contact me directly if you're a masochist.
Thank you.
We'll be happy to make that information available to anybody that reaches out to us. Yeah, thank you again. And
Thank you.
Thank you very much. Bye.
bye.